Galaxies are sprinting apart, yet clusters stay locked together. The short answer is gravity, strengthened by vast dark matter halos. We feel this glue through motions and lensing, not direct light. Keep this picture in mind as we talk tonight. Space expands overall, but bound islands resist that stretch. Those islands are galaxies, groups, and titanic clusters of galaxies. They last for billions of years because their gravity wins locally. Some structures never form at all because expansion thins them out. The balance is scale dependent and density sets the winner. Gravity beats expansion on small enough scales, thanks to dark matter. Let's trace how that balance works in real, simple numbers. A star skims the Milky Way's glowing disk during a quiet night. Gravitational binding energy is the energy required to tear a system apart. Without enough binding, orbits loosen and the structure flies apart. Gravity pulls inward while motions and heat try to push outward. Stable structures settle into balance, called virial equilibrium, between pull and push. In that state, twice the kinetic energy roughly cancels the potential well. You can feel this with a simple rule of escape speed. If speeds stay below escape speed, gravity keeps everything bound. For our galaxy, stars cruise near 220 kilometers per second. The escape speed near the Sun is about 550. Orbital periods are long, yet the binding persists for many orbits. One sentence recap: speed below escape means safe, speed above means gone. This balance survives encounters because gravity redistributes energy during interactions. Random motions heat slightly, while gravity deepens the shared potential well. After a disturbance, systems relax toward equilibrium over a crossing time. The Milky Way crossing time is roughly 200 million years, so the picture is simple, despite the math beating underneath. Gravity supplies cohesion, while motion tries to escape the well. If the well is deep enough, the structure endures for ages. Locally, that depth beats the universe's steady outward stretch. Now zoom out past the stars into the galaxy's invisible outskirts. A dark matter halo is a vast, diffuse cloud of mass. It extends far beyond the visible disk, shaping every orbit. This matters because the halo's gravity outweighs the stars combined. Most galaxies sit inside halos that outweigh them by a factor 10. Gravity from this halo keeps rotation curves flat, even at edges. If only stars were present, speeds would fall with distance. Lensing gives us a map by bending light around the mass. Arcs around clusters trace where the gravitational well is strongest. In practice, particle orbits stack to build a stable, self-held halo. They slow in dense regions and they speed in sparse ones. Collisions are rare, so the system behaves like a fluid potential. Simulations grow halos with a universal, cusp-to-tail density shape. Example in real terms, the Milky Way's halo is enormous. Its mass is near 1 trillion suns, spread across 300 kiloparsecs. A rich cluster halo can reach a quadrillion suns across megaparsecs. Stars and gas ride inside like boats within a deep harbor. As long as the harbor is deep, storms cannot eject them. So the hidden skeleton of dark matter holds the stage together. It provides the depth that lets galaxies survive for eons. 6 billion light-years away, galaxies drift with the Hubble flow. A bound system is one where gravity cancels cosmic expansion locally. Otherwise, expansion would thin every structure to mist. Outside the well, space expands, carrying unbound objects ever farther. Inside the well, orbits close and the fabric hardly stretches. Dark energy accelerates expansion, but not inside deep, compact wells. There is a boundary where the tug and the drift balance. Astronomers call it the turnaround radius for a given mass. Beyond that radius, expansion wins and escape becomes the default. For the local group, that radius is about 1.3 megaparsecs. The Milky Way and Andromeda sit bound despite the global stretch. They will merge in roughly 4 billion years, then settle again. Rule of thumb, denser than the cosmic mean by 200 stays bound. Dark energy changes distant fates, but not the deep interior. In a far future, only bound islands will remain within sight. Net result, binding beats the background where gravity makes a pit. Where there is no pit, expansion sweeps material into filaments. Those filaments feed halos, while voids grow ever more empty. Structure survives by staying dense enough to ignore the cosmic wind. Shift to a colossal cluster, where hundreds of galaxies swim in plasma. The intracluster medium is hot, thin gas filling the cluster's volume. This matters because this gas carries pressure that helps steady the core. Gravity holds the gas and the gas adds cushion against sloshing. Shocks from mergers rumble through, heating the medium to tens of millions. Temperatures reach 10 to the power of 8 Kelvin in cores. Magnetic fields thread the gas, guiding particles and damping turbulence slightly. Jets from central black holes inflate bubbles which stir and heat gently. In practice, pressure gradients support weight, while radiative cooling drops heat. When cooling wins locally, cold clumps rain back and sustain the cycle. X-ray light reveals ripples, edges, and bow shocks from past crashes. The Sunyaev-Zeldovich effect shows the pressure by dimming background microwaves. Example, the Perseus cluster shows bubbles spanning tens of thousands of light years. Those bubbles carry about 10 to the power of 60 joules. That energy offsets cooling and helps the core avoid runaway collapse. Bottom line, gravity grips the gas and pressure spreads the load. Together, they keep the center calm for billions of patient years. Now watch a small galaxy falling toward a massive cluster's heart. Tidal forces are the uneven pulls that stretch objects across a field. Tides can strip stars and gas from satellites on close passes. The side nearer the cluster feels more gravity than the far side. Streams of material peel away, tracing arcs that wrap the host. Meanwhile, dynamical friction slows the satellite by stirring background particles. It transfers orbital energy into random motions, like wake in water. The satellite sinks deeper, then merges, and the host grows heavier. Afterward, debris shells ripple outward, then fade into smooth halos. In practice, mixing spreads energy among many orbits, smoothing sharp features. Relaxation moves the system toward equilibrium over a few crossing times. Example, a dwarf may lose 90% of stars in one pass. Its core can survive and then become the cluster's faint halo. One sentence recap: tides unmake details while gravity preserves the whole. That is why clusters look smooth, despite messy, violent assembly histories. Net result: mergers roughen, but they rarely break the deep well. The reservoir deepens, and future arrivals find even fewer escape routes. Over time, debris fades, leaving ghostly arcs in starlight and gas. Drop into a galaxy's core where a black hole launches jets. Feedback is energy returned to gas by stars or black holes. That energy stirs gas, regulates stars, and carves cavities in halos. Supernovae push on gas, and jets inflate buoyant, radio-bright bubbles. This energy rarely unbinds the halo because gravity's well is deep. Instead, it lofts gas, cools, and returns in a gentle cycle. Stars form, explode, and enrich the medium with heavy elements. Then gravity gathers the enriched gas back toward the center again. Example, a single outburst can deliver 10 to the power of 61 joules. That is enough to heat cluster gas across hundreds of thousands of light years. Star formation responds, dipping down, then rising as gas cools again. In practice, feedback adds turbulence that delays runaway cooling and collapse. But the halo's depth sets the stage and keeps material bound. One caution: too much energy can blow out gas in dwarfs. Small wells lose gas, while big wells recycle it many times. Bottom line, feedback sculpts galaxies without erasing the dark backbone. Evidence for all this comes from maps, echoes, and careful simulations. Weak lensing maps show mass where light is sparse or missing. Strong lensing paints arcs that ring the very deepest wells. Cosmic microwave background ripples fix the seeds that later collapsed. Those seeds are tiny overdensities, about 1 part in 100,000. Baryon acoustic oscillations mark a preferred scale near 150 megaparsecs. Surveys find that scale imprinted in galaxies across cosmic time. Simulations grow a web of filaments, nodes, and deep halo basins. Their halos match observed counts once feedback is added realistically. Example, the dark matter fraction inferred is near 85%. A typical cluster mass reaches a quadrillion suns within a few megaparsecs. Velocity dispersions hover near 1,000 kilometers per second in clusters. X-ray temperatures reach tens of millions, confirming the deep gravitational wells. Tiny tests strip light from images and the mass map remains. That map is drawn by lensing alone, matching the dark scaffold. On small scales, binary stars show gravity's rules with exquisite precision. On vast scales, galaxy flows trace where wells pull against expansion. Net effect, every test points to the same, deep potential backbones. So the picture is robust, across methods and across eras. We see the glue's effects everywhere, even when light is scarce. Remember that opening paradox: expansion everywhere yet clusters stay intact. It resolves because gravity builds deep wells that ignore the stretch. Dark matter supplies most depth, and pressure helps steady the cores. Mergers roughen details, but the backbone endures for billions. If that picture clicked, share this with your favorite space friend. Bottom line, dense islands hold fast while the sea keeps stretching. Thanks for hanging out under the cosmic web tonight. See you in the next sky story, same quiet wonder.